Hello everyone, thank you for joining me for my presentation called RISC-V Tracing, What is Different? My name is Nino Vidovic. I'm a software engineer at SEGGER Microcontroller. I'm the product owner of the JTrace product group. You see it in the middle down there. If you want to watch more talks about this, I've done them in the past in the emBO, so you can find it on the YouTube channel. I'm also a coordinator of the SEGGER University Partnership Program. So if you're in some way working at an educational facility and looking to get your hands on professional tools and want some partnerships with us, feel free to connect with me on LinkedIn, or just come up to us to our booth in the conference room, and we can see if we can find some cool project that we can do together with your faculty. And yeah, apart from tracing and university stuff, I also do working in the departments for software development tools and analysis tools. Some of them are Ozone, our universal debugger, System View, our software instrumentation analysis tool, and Embedded Studio, our IDE with our own C and C++ toolchain and libraries. So if you're interested, check them out. They can be all tried out for free. And what is my motivation for this talk? Well, as you see, I work in the JTrace department, and in the last couple of years, RISC-V has getting more attention. And as I was implementing a decoder for the new trace standard that RISC-V group was implementing, I thought I have to document it anyhow, so why not make a talk out of it? So I hope you guys find this interesting and maybe learn a thing or two. So what will the talk be about? So first I will talk a bit about tracing. What is tracing? Then we will talk about the state of the art. Here, state of the art, I will tell you what ARM is doing, because currently ARM simply has the biggest market share for trace-capable target devices. This is why I will focus on ARM here. Then I will compare this to what RISC-V is currently standardizing and implementing. Then I will put the spotlight on some of the components, how they're working, what features you have there. And then we have a little summary and a conclusion. So what is tracing? This is what Wikipedia says. Essentially, it is some form of logging. You're trying to figure out how your system has operated or has been running. There's different differentiation done here between event logging and low-level tracing or bare metal tracing, where event logging would be something that a system administrator would see, for example, on a Linux server, where you're looking at the system as a whole and you're looking at the high-level logs. But today I will focus on the low-level tracing, where you trace your own firmware or application or whatever, and where you ideally want to know everything about your system, right? From the reset handler on to all your tasks that are happening and so on, and how the resources are used. So yeah, we will focus on this one in this talk here. So generally there are two different trace types. One is software tracing, one is hardware tracing. Software tracing is what you all are probably familiar with, is your simple printf. This is already tracing, because you can write, started this function, I calculated this result. So you have some feedback from your system, you can read it, you know what may have happened on your system. The biggest difference between software and hardware tracing, though, is that one is always intrusive, the others can be non-intrusive. This means that when you try to do software tracing, you always add some code to your code base. That means that some of the CPU cycles, some of the resources you're using is being used for this tracing feature. With hardware tracing, you don't have this problem. This is a built-in chip feature. It simply listens in to the core's execution unit and is just pushing out the data and telling you exactly which instructions have been executed. But both have their use cases, and with some more elaborate printf, you can do something like you see here with System View, where you can have all your context switches and some beautiful analysis graph and still know what's happening on your system. But yeah, we will talk about hardware tracing here. There are two big variants here, or two different types again. One is the on-chip trace buffer, so your target device itself has some kind of RAM or something where the data is dumped to. You can read from it and then know the history of your application. And the other is pin tracing, where you have an extra pin interface additionally to your debug interface, where the data is simply being streamed out to your host PC or debug probe or whatever and analyzed on host side. So here are the general ARM core side trace components. So everything that's related to debugging, tracing, and stuff is called core side at ARM. It's their trademarked name for this. And the main components that have to do with tracing is the trace encoder, the trace buffer, funnel, and port. And the hardware interface that we have here is the debug interface. So you have JTAG or SWD, which can be used for this buffer tracing type, where you just read from a RAM. And and then the other interface is the trace pins. We have additional pins that you have implemented on your board. But that way you can stream the data out continuously while your target device is running. On the right, you can see such an example pin interface on a trace reference board. And you see on the pin out, you have your standard SWD and JTAG pins. And this interface is also MIPI 20 compliant. So it's standardized over a very widely used alliance that has been used for many, many years on all kinds of hardware designs. So it's very, very well established. So we have different kinds of trace buffers and trace coders for ARM. On the trace buffer side, we have the micro trace buffer, the embedded trace buffer, and trace memory controller. They're available simply on different architecture levels, essentially. So they started off with the micro trace buffer and then evolved on. With trace encoders, we have the trace encoders are the ones that create the trace information. So there's the embedded trace macro cell, usually found on Cortex-M or R. Program trace macro cell is on Cortex-ACE, on the bigger ones, and then you have the instrumentation trace macro cell, specifically on Cortex-M. Then you have the trace funnel and trace port interface unit. In general, maybe to add to the trace buffers, so as I said, it's always some kind of RAM. Sometimes it's dedicated RAM, so you can't use it for your code. It's really just a RAM area that is only being used for this feature. But it can also be shared. But when you're using shared RAM, you always have the danger of overwriting your application with trace data. So this is something you have to keep in mind depending on which variant you are using. So how does this look like in a typical ARM system? Here's an example from the ARM manual for the Cortex-M85, the newest architecture from ARM. So what we see here is the processor core. This is connecting to the ETM, the trace encoder. This is always a unit together in the processor unit level. And this is now streaming out over the trace bus, to a replicator where the same data is simply being pushed to embedded trace buffer and a trace port interface unit, which is the pin interface. And it goes out to a trace probe or whatever. One element you don't see here is the funnel I showed in the last slide. The funnel would be used if you have multiple trace encoder sources or multiple cores even. So that funnel would be placed between the bus and the replicator somewhere here. So you could have multiple cores that all stream data and then they are all joined together here. As I showed you, there are different types of trace encoders, and they all offer different quality of information that you get from them. So you always have some kind of trade-off of how deep the system insight is and how much maybe pins you're sacrificing, or how much more expensive maybe the silicon is has to be produced. So on the lowest level from what ARM offers, you have this ITM system. You maybe have used it. The pin that's used is the SWO pin usually. So this is just an event-based PC logging. So your program counter simply gets put out either periodically or on certain events. So you get on certain events information where your program has been, and technically you can do code coverage with that if you let your program run for a very, very long time. So at some point, statistically, every instruction at some point should have been sent out. But yeah, it's nothing you really want to rely on. So it's more reasonable to use one of the gapless variants, which starts with the MTB. So here you already get the gapless information really from start of your application to wherever you have placed your breakpoint or whatever. And but this was the first introduction on Cortex-M0 Plus microcontrollers. They did not put no compression in there, and everything is output. So even inferable branches and stuff like that would end up in this trace buffer. So not a lot, so the time you could look back in your code and your backtrace was not that big. So this was changed with ETM v3 and PTM. There they added some additional compression layer. That way much more trace data could be fit into the same payload. But from this point on, you need to know what application you're running on the target device, right? Because now this compression relies on you knowing the ELF file or the instructions that are executed in the system to be able to decompress the stream. And in the end, ARM introduced ATMv4, which is even more compressed, essentially, and more modern with some more features. And on the left, you can see what kind of information you could get for this. So code profiling, you can have the backtrace, the instruction trace. You can go back in time and find out what has happened on your product and in your firmware. And you can do code profiling as well. So timing requirements. So we have talked about buffers, encoders, and all these components. And now let's talk about this pin interface. ARM has had to define some pin interface so that silicon vendors and board producers can rely on some standard that will be supported by some trace tools. The specification says, okay, you have a CPU clock, then you have the trace clock that is output via the pins, and the trace clock is half the speed of your CPU clock, just to be able to use slower GPIOs to still trace fast CPUs. That was the idea here. But to still keep up with the incoming trace data, they made a double data rate. So on every flank of the trace clock cycle, we are sampling the trace data lines, and the trace data is 90-degree phase shifted to the trace clock, so you don't come into some sampling issues where the gaps got too close with jitter or similar. Here are the specifications, and from the specifications you can see with 2 nanoseconds as a minimum. This means that you have a maximum trace specification constraint trace standard that says you can do maximum 100 megahertz. Of course, you can do faster GPIO, implement faster GPIOs. Then technically a probe vendor could tell you, well, you're out of spec and you're out of luck. We don't do this. We support up to 200 megahertz. And in reality, the fastest GPIO for trace clock I have seen was like 130 megahertz. But everything's faster than that becomes very hard to handle on your board, on shielding, on the GPIOs. The chip gets very expensive, so silicon vendors will not implement it and stuff like that. So ARM has put some quite reasonable maximum here with 100 megahertz. And yeah, so far nobody has really gone over like 200 or something. Okay, so that was ARM. What is RISC-V's plan? So what I will show you now is based on the information you can find on GitHub from the 9th February 2023. There have been some changes in this spec since then, but nothing crucial that I will talk about. I'm also part of the standard group that they're like meeting once a week, and we, from our perspective, we're trying to avoid implementing things that will make our customers unhappy. So far it's going good. And yeah, and the plan that they had was, okay, we want to make sure that we have a that using pin interface, the MIPI20 that we saw earlier, that is already standardized by ARM, so people are familiar with it. Then the other one was, okay, we want to make this compatible to a standard that people from other architectures might know, which is the Nexus Trace standard. Then they are implementing 2 different variants of trace encoders. Some of you may know Sci5. Sci5 is essentially the umbrella corporation from the RISC-V Foundation, which is pushing the new features and implementing a lot of the open source stuff here. So they proposed the Nexus Trace encoder, but there was also Siemens. They were saying, okay, we like your Nexus Trace, but we want to do something that's called efficient trace, and we think it's better. In reality, they're both pretty much the same. So, yeah. But today I will focus on the Nexus Trace standard, simply because this is the only standard that was fully implemented first and published, and because it's the whole interface from encoder to the trace pins, everything is called Nexus in this area. But what you can do is you can replace your encoder. That is why this Siemens encoder is also in the standard. So you can choose which encoder you want, but the rest of the flow will be the same. And yeah, one of the goals was, okay, let's find a better compression than ARM. So let's see how they do. First, let's talk about the Nexus standard. This was an IEEE standard. It was started in 1998 by some bigger silicon vendors, and they wanted to have a modern, standardized debugging interface for embedded systems. Some of you may be familiar with such debug systems, and it was actually this IEEE standard committee was disbanded in 2020. Not because the standard is bad, but they were not adding any features for more than 8 years, and they were saying basically, we were done with it. Everybody in the committee was happy with the feature set, and nobody wanted to expand anything, and they said, okay, we will freeze it. The standard is open. Everybody can use it and adapt on it. So yeah, that's why it was disbanded for now. So yeah, and what does this standard also implement is the Nexus Trace, which is a substandard inside of this IEEE standard. And this implements program trace, or defines program trace, data trace, and ownership trace. Program trace is what you saw on the screen earlier with the the backtrace information and the whole application information that has the instructions that have been executed on your system from the beginning. So this is what you program trace, so you know what happened at any time. Data trace adds another information layer here, because with program trace, you, for example, don't know what was loaded in your CPU registers when you do loads, stores, and stuff like that. So you only know the instruction that was executed, but not the data access. So what with data trace is added is they also stream out every load and store from your memory. And then there's ownership trace. This is for context switches for an OS or something, for example. Yeah, generally Nexus specifies 4 different implementation classes. Class 1 is your standard JTAG interface with, start, stop, flashing, breakpoint, stuff like that. Class 2 defines ownership trace and program trace. Then we have class 3, that's data trace. And class 4 adds, I have to read this because it's a bit complicated, memory substitution via Nexus port and trigger substitution via watch points. Everybody knows what I mean. But generally, ARM and RISC-V define class 2 as default with an optional class 3 for data tracing. And as I said, Nexus defines the whole spec from the encoder to the pins. It also defines a message protocol, which I will explain in a minute. So let's talk about the Nexus Trace components. Again, we have a trace encoder. Here in the Nexus Trace encoder, they have again 2 variants. One is the branch trace messages and one the history trace messages, where the history trace messages are a superset of the branch trace messages. So if you're saying, either just need rudimentary trace support, you implement the first one, and if you need some additional bandwidth with extra compression, you use the second one. Then we have so-called trace sinks, which is simply output sources, essentially, which are supported by this encoder, which is your SRAM, system memory, trace pins, and a funnel. And we have a trace funnel again. And there on the right, you can see, again, how this is interconnected. So we can have multiple trace encoders, where one encoder is per core. We have a funnel that collects all this, and then a trace sink that outputs this anywhere. One interesting feature here, though, is that this funnel from RISC-V is all, again, interconnectable to other architecture types. So you could have technically RISC-V and ARM tracing on the same SoC and then put it in the same funnel and use the same pin interface. So this is technically supported. Time will tell if anybody will do it. So how do the components compare? So on the left, we have Nexus Trace from RISC-V, and on the right, ARM core side tracing. So we have the two different encoders, which is comparing to eTMV3 or eTMV4. Then we have the trace sync, which is something RISC-V SRAM tracing, which is like a trace buffer. Then we have the system memory tracing. This is an advanced way of buffering your data, because now you can use any type of system memory instead of a dedicated one. So you can have some DDR RAM that you have loaded up and then just dump the data in there. And then you have the trace sync, pin trace sync, which is the TPIU on ARM. Trace connectors are also identical. Here, again, the same pinout, where 4 data pins are implemented. The minimum implementation is 1 data pin. And there's also the MIG-38 connector, but this one exists also for ARM. So this is not RISC-V exclusive. Just putting it on a slide here, so you see that both connector types implement trace pins that can be used for different bandwidths that are maybe required with your system. Then let's go to the features. Of course, we have instruction tracing, like that's the main point here. Then with BTM, as said, we have this standard branch tracing. With HTM, we get extra compression. Then we have this ownership trace. We have triggers, so you can even decide to say, okay, I only want to trace certain memory areas that are interesting to me. If you have, for example, not such a big bandwidth or something, or too little pins, then you can still trace only certain areas that are hotspots for you. You have stalling. Stalling is a feature where you can, if your interface is risking overflow, where you would lose trace data, you can enable this. And every time when the overflow is risked, it will temporarily halt your CPU until the pipeline is cleared and then continue. This, of course, makes this intrusive again. So this is something to keep in mind. But it's a nice trade-off. If you really don't have the pins or something, then this is the way out if you still want to have some kind of system insight via hardware tracing. Then we have different sync modes where you can, because the trace stream has to be synced from time to time. And here it's even configurable, so you can either turn syncs off completely, have them count trace messages or packets, have to just count CPU cycles or the half-words instructions that have been executed. And we have optional data trace or timestamps. Funnel features. As we saw on the graphics, it combines multiple trace sources. The spec says input channel priority is implementation defined. This is always great as a tool vendor if you read something like this. And they recommend a round-robin principle. Yeah, this is what the spec says. Optional timestamp generator, this is a cool thing, I think, because now you're not only matching timestamps to your trace packets that you generated in your encoder, but instead you can also track when they have been joined by the funnel. So it gives you an extra analysis layer, so this was interesting. And again, trace, you can have multiple funnels, one after another. If you have some crazy multi-core setup, you can do that as well. Let's go to the message format. We have variable and fixed fields. It's always the nice thing of the message. So it starts with the T-code field, the transfer code, and ends with the timestamp field. So for me, as someone who has to write a decoder of this, it's very easy to analyze because you always know how such a message starts and how it ends. Here the message in ARM world, this is called trace packet. Here they call it messages, same thing. The standard implements 6 bits, so we have 64 messages that can be used. 12 are in use, and with HTM trace, BTM uses 8 packets. So there's plenty of room of improvement here. The message format looks like this. Here's an example for a so-called direct branch message. So every time you have a direct branch, this is output. You get a transfer code, it's just number 3. Then message source information, which tells you from which trace encoder on your board has this message come from, and then you have an instruction counter, which tells you how many instructions have been executed since the last sync point, and a timestamp. The transmission protocol looks a bit painful. I had no better way to display this, but on the next slide, I hope it gets better. But in general, you have a message start and out and a message data out. Message start and out simply tells you, okay, where am I within a message? And the message data out tells you the payload that's being sent out by the core. It's split up into slices. So you always have 6 bits for the data out and 2 bits for the message start and out. That way we always 1 byte aligned. And this is beautiful because it doesn't matter if you implement 1, 2, 4, 8, 16-bit trace interface on your pins. It will always work and can be sampled nicely without any overhead. So this is quite clever. This is how the transmission protocol then looks for a direct branch message again. So we have first simply do not care, because we come either from idle or from a former package. Then we have the 2 bits here that say, okay, start of message. Then we first get the 6 bits of the T code that tells me what it is. Then we have the source, then the instruction count. Here we know, okay, variable length field end, we paired with zeros. We now get a new slice with timestamp info and end of message. And then the next one starts, or we have idle. So pretty straightforward. So yeah, the summary. What we saw is RISC-V has implemented a Nexus compatible substandard, including the connectors. So if there's a pretty good chance that this will be supported quite widely. The message format is fairly expandable. As said, we are only using 12 messages so far, and with these 12 messages, you have full program trace and ownership trace. So you have all the other messages left over for either other features or data tracing, for example. The compression level is also very configurable, so BTM would be something without much compression, but you can have different configuration levels that you can use. Then we have this very flexible funnel interface that can be not only used in different sync combinations, but also with other architectures, and a very nice and sleek and simple transmission protocol. So how does this compare? What is better, or good or better? I will compare here again to the ARM stuff that I've shown before. Yeah, it's standard compatible, so there's a good chance that a lot of tool vendors will simply support it because it's an open standard and it's well documented and yeah, has been proven over time that it's a good standard. It has a more compact transmission protocol. So we have 2 bits of start-stop stuff going on per slice. So we have 25% overhead here for our sampling protocol. With ARM, it's more in the area of 30 to 40%. So we are better here. It has potential for fast analyzers because, as we saw, we always have this condition T-code start, timestamp at the end. So as soon as I have parsed the T-code, I can chug it to some of on my host PC to a multi-threaded to one of the threads, and then let the analyzer handle it and grab the next message and stuff like that. So there's a good amount of multi-threaded optimization that can be done here. Yeah, we have many configuration options for implementers. So for silicon vendors, they can implement this however they want, and they will still be, still can be standard compatible. It can be used with other trace types, third-party trace types. Yeah, we have the MIPS-20 standard trace bin interface. The messages can be expanded. So if you say, okay, some features, some system inside is missing for me, I can add this. And we have less forced sync packets than ARM. So overall, doesn't look bad, right? Well, there's also some things. Some of these are it's just my opinion, but it's what we have. So yeah, what's better or worse? Yeah, I said, on the one hand, I say it's a great thing that you can have message supersets. On the other hand, it's horrible that you can have trace message supersets, because you're defining a standard, right? And now if you allow implementers to add messages as they like, at some point mistakes will happen. And now the question is, how carefully worded is such a standard, where then you can say, no, you did it wrong, you're not standard compatible, tough luck. Because as soon as you no longer follow these rules of the standard with the T-code, timestamp, and fixed fields, configurable fields, whatever, you will no longer be compatible to the decoders that the trace probe vendors are writing. And then they have to, in worst case, make a completely new decoder just for your wrong implementation of the standard. So this is something that we have to be careful with. The compression is sometimes too good for life, and this is what I mean here. Is one of the features that are pretty nice is that you can stream this information out live to your host PC and do the analysis live here. And while your application is running, you can already see certain hotspots, right, in an application where counters are going up, areas get red or whatever. Now the problem is, if you have a very, very compressed trace stream, you're no longer getting continuous data about what has been executed, but the trace stream is the encoder is telling you, well, I'm doing a memcopy loop for the next 20 million cycles. You already know where I'm going to jump to. I will tell you after the 20 million cycles where I ended up. So on the analyzer side, on the host PC, it will suddenly be a 0, and then suddenly the counter will jump up to 20 million and you don't know what happened. So it can look weird sometimes. So this is maybe one of the drawbacks of too good compression, that the live features can be looking more choppy than without compression. Yeah, but again, same with trace messages. So you allow a lot of configuration options for implementers. Can be a good thing, can be a bad thing. For example, if an implementer forgets to make a feature that is optional, that you can configure it via the registers. Sometimes they hard code it into the chip, and then you can change it anymore. This is a problem, of course, if you have implemented a certain standard. No auto detection of trace components is a bigger one. This is something that ARM supports. So when you connect to a target, you already know all the core sets and components and can configure them. With RISC-V, this is a manual job. It is planned, but not in this standard, so I have to write it down here. Then we have the wrongly sampled data is harder to detect. As we saw, the transmission protocol is very simple, but there's also this catch that you only have essentially 2 bits where you can check if the transmission has worked or not. So if something gets wrong in the payload, you don't know, because this is your payload. But you have only two bits for checking if transfer has happened correctly. And yeah, we're with ARM tracing, you get some frame information. So you have a bigger overhead, but you have some frames you can check against, so you have a higher chance of finding set errors. And as we saw, the funnel priority is implementation defined, so we will see what that means. So, conclusion. Generally, I think RISC-V has done a very good job here with our competitive open trace standard. The ratification should be done by Q2 2023. Yeah, easily expandable. Base components are very good, well comparable to what ARM is offering. Sometimes they're better, but we don't have silicon yet. So I have also here just an FPGA board. There's no silicon. So We will see how this translates to the real world. How does this look for our company? So 2020, we have done a trace buffer support. I think since 2018 or 19, we are supporting debugging in general. Yeah, we've launched this product last year. The JTrace here, this is just a demonstrator board, which I've brought with me. So if you're interested in a live demonstration, I will be in the conference room. You can ask me anything about tracing there if you want. We currently support this BTM Nexus Trace. HTM is also already finished, but here's the thing, things are changing still. The standard is not frozen yet. So if we release now something and then they change the standard again, we have to patch it, and then we have versions out that are not really supported and stuff like that. So we're currently waiting with the HTM release until the standard is frozen and we know that what we have implemented will not be changed anymore. And yeah, we will see what the market brings, because these two open standards are, of course, the preferred solution by the RISC-V group, but the RISC-V enables you to use anything with the cores. You can slap on also some other trace interfaces there if you want to. So yeah, essentially we made the egg and we're now waiting for the chicken to hatch, right? So let's see what the RISC-V world will bring us. All right, thank you. That was it.